Hi, hello, welcome back. Okay, so for this video, we are going to discuss AM receiver circuits. Okay, so we're going to discuss some of the mostly used circuits in AM receivers, whether they are in their discrete form. Okay, so what do we mean by discrete form? So we're going to build them from real individual transistors, resistors, capacitors, inductors, and so on, or maybe in a form of an integrated circuits wherein the circuits are already inside an IC chip. Okay, so to start with, okay, so we will be discussing about what are the types of RF amplifiers that we are using. Okay, so actually, we have already discussed the different stages in AM receiver. Okay, so from the antenna, from the receiving antenna up to the speaker. Okay, so we will be discussing each stages and what types of circuits are being used by each stage. Okay, so we will be starting with the RF stage. Okay, so initially the signal will first encounter what we call the RF stage. So the primary purpose of an RF stage are selectivity, amplification, and sensitivity. Okay, so an RF amplifier is a high gain, low noise tuned amplifier that, when used, is the first active stage encountered by the received signal. Okay, so by the way, our received signal is your AM envelope. Okay, so having a very, very high frequency in the radio frequency range. Okay, so we have here there are times, okay, so there are times that some circuits doesn't have an RF amplifier in their RF section. However, having RF amplifiers will give us this following characteristics. Okay, so if we have an RF amplifier in the first stage of our receiver circuit, we can experience low thermal noise, low noise figure. So these things we have already discussed from the previous videos. Okay, so we have moderate to high gain, low intermodulation and harmonic distortion. So most particularly if our amplifiers are working in the linear operation, okay, we have moderate selectivity and high image frequency rejection ratio. Okay, so um, AM demodulator. So the main function of AM demodulator detects amplitude variations. Okay, so detect amplitude variation since it's amplitude modulation. So there is a variation in the amplitude. So this detects amplitude variations in the modulated wave and converts them to amplitude changes in its output. Okay, so the two most important parameters for our receiver is amplification and noise figure. Okay, consequently, the amplitude variations that were caused by noise are converted to erroneous fluctuations in the demodulator output. Thus, the quality of the demodulated signal is somewhat being degraded. Okay, so it says here that the more gain a signal experiences as it passes through a receiver, the more pronounced the amplitude variations at the demodulator input and the less variations caused by the noise. Okay, so actually noise voltage plays a very vital role in our received signal. So as if you will remember, okay, so if you would remember, our noise voltage is given by the formula. So what is of the formula for our noise voltage? So Vn, or our noise voltage, is equivalent to the square root of 4 multiplied by R multiplied by K, and we have here your B. Okay, so this means that the noise voltage is proportional to this different parameters. So what are those different parameters? So it is proportional to the temperature, okay? So to the bandwidth and to the equivalent noise resistance. Okay, so in order for our signal to be not degraded, we have to at least minimize. If we cannot totally eliminate, okay, so at least we have to minimize these parameters, because if we somewhat minimize these parameters, our thermal noise will somehow be reduced. Okay, so how are we going to minimize our temperature? Okay, so what will be our solution regarding our problem about temperature? Okay, so usually AM receivers uses uh, artificially cooling or coolant, okay, at the front end of the receiver, with either using air fans, okay, or even liquid helium in a more expensive type of receivers. Okay, so that is our solution for the temperature. How about the bandwidth? Okay, so we will be improving the bandwidth if we're going to make use of tuned amplifiers and filters with with a very very narrow bandwidth. Okay, so how about the equivalent noise resistance? How are we going to improve your equivalent noise resistance? We usually use specially constructed solid state components for the active devices. Okay, so instead of using actual resistances, we are make in lieu of actual resistances or resistors, we make use of active devices. Okay, so we have here the more gain a signal experiences as it passes through the receiver, the more pronounced the amplitude variations and the demodulator input, and the less variations caused by the noise. Okay, always remember that noise is also changing in its amplitude. So your receiver might be confused whether that is an actual signal because it is detecting change in amplitude, while noise is also characterized with changing in its amplitude. Okay, so the narrower the bandwidth, okay, so how are we going to improve the bandwidth? So the narrower the bandwidth, the less noise propagated through the receiver and the less noise demodulated by the detector. Okay, so one important aspect also in the first part or in the first stage of our amplifier or receiver circuit is the noise figure. Okay, so this is a measure of the noise added by the amplifier, because even your amplifier is capable of introducing noise to our system. Actually, if the received signals has noise in it, okay, so we are not just amplifying the signal, we are also amplifying the noise. Okay, so therefore your noise figure must also be improved. Okay, so it must be improved or it must be reduced, okay, by reducing the amplifier's internal noise. Okay, because even the amplifiers, they also contribute to our noise. Okay, so we have here intermodulation and harmonic distortion. Okay, so these are forms of nonlinear distortion that increase the magnitude of the noise figure by adding correlated noise to the total noise spectrum. Okay, so the more linear an amplifier's operation, the lesser, okay, so the more we make your amplifier linear, the lesser your non-linear linear distortions, okay, because intermodulation and harmonic distortions are characterized as non-linear distortions. So how are we going to solve these problems, or if not eliminated, at least reduce the problem? So by using a more linear, or by operating your amplifier in its linear form. Okay, so image frequency reduction by an RF amplifier, we usually combine this usually combines with the image frequency reduction of the preselector to reduce the receiver bandwidth sufficiently to help prevent the image frequency from entering the mixer and converter stage. Okay, so our RF amplifier, the first stage of our receiver circuit, has a moderate selectivity. Okay, in moderate selectivity is all that is required in our RF stage. Okay, so this is an example. Okay, so this is one example of our bipolar transistor RF amplifier. Okay, so as we can see, when we say RF, okay, so I will be repeating this. RF is a relative term. So we do not have actually an exact value for an RF. So it depends on what is our application. Okay, so an RF is a relative term, and it simply means that the frequency is high enough. Okay, the frequency is high enough to efficiently radiated by an antenna and propagated through free space by an electromagnetic wave. Okay, so it depends on the value. So for example, again, for AM, so what do we mean by AM? So the RF frequency that we are referring to for AM is your 535 to 1605 kilohertz. Now, if we talk about FM, we are now referring to different value of RF, which is from 88 to 108 megahertz. Okay, so your RF considerations may also be applied to IF amplifiers. Okay, so actually, when we are talking about amplifiers, they usually have the same designs. Okay, so we will just be changing some of the values because we are changing the cutoff frequencies for each amplifiers. So take for example RF amplifier. So we will be designing this circuit in such a way that it will be functioning within this specific range of frequency. Now, we can also have this same design but with a slightly lower frequency, and then that is already considered as an IF amplifier. Okay, so RF considerations may also be applied to IF amplifiers. So we will be discussing IF amplifiers later. And those are your neutralization, you have your filtering, and you have your coupling. Okay, so if we're going to look at uh, this circuit here, okay, so we have here your CA. So where is our CA? So we have here your CA, your CB, your CC, and our L1. Okay, so this comprise your coupling circuit for our antenna. Okay, so your radio frequency waveform, okay, so your RF waveform will be coming from an antenna. So therefore, this we need a coupling circuit for that. So that will be provided by your CA, CB, CC, and your L1 here. Okay, so your Q1 here, okay, so our transistor Q1 here is biased as a Class A amplifier. Okay, so why do we bias your Q1 here as an Class A amplifier? Okay, so because Class A amplifier reduces nonlinear distortion. So as we all know, Class A has a characteristic of linearity. Okay, so your collector circuit here, the output, okay, so the collector circuit here is transformer coupled. So this is our transformer coupling, okay, to the mixer or converter stage. So actually, this is the following stage of your RF amplifier stage. Okay, so this is double tuned. Okay, so later we will be discussing what is the meaning of double tuned for more selectivity. Okay, so we have a what we call feed through capacitors. Okay, so our feed-through capacitors offers less inductance, which prevents a portion of the signal from radiating from their leads. And usually those are your CX and our CY. So this is our CX and CY. As you can see, these are our RF bypass capacitors. They are specially constructed feed-through capacitors. So our CN here is neutralization capacitors. Okay, so because a portion of the collector signal is fed back, okay, as a feedback, so it is fed back to the base circuit to offset or to neutralize the signal fed through the transistor collector base to prevent oscillations. Okay, so we do not want oscillations to happen, okay, because we are not producing any waveform here. So to do that, we have here your neutralization capacitor. Okay, so our CF here, so where is our CF here? So this is our CF. This is in conjunction with our neutralizing capacitor. So this forms an AC voltage divider for our feedback signal. Okay, so we call this configuration as off-ground neutralization. So this is a type of a neutralization configuration. Okay, so we have here another type of an amplifier circuit, and we call this as a DMOSFET RF amplifier. The function is the same, okay, so the purpose is the same. The only difference is that instead of using bipolar junction transistor, we make use of dual gate, okay, dual gate field effect transistor, or what we call a DMOSFET. Okay, so if you can still remember DMOSFET, it stands for depletion enhancement metal oxide field effect transistor. Okay, so what is the advantage of using FETs instead of BJTs? Okay, so FETs are characterized as high input impedance and low noise. Okay, so as it has a square law device characteristic, okay, that generates only second order harmonic and intermodulation distortion components. Therefore, comparing it with BJT, it produces less nonlinear distortion. Okay? So another type of RF amplifier circuits that you might be encountering is what we call a cascoded RF amplifier. So a cascoded RF amplifier is a type of a compound configuration wherein we are combining, okay, so in this case we are using FET here. So this is a common source, okay, and a common source and a common gate. Okay, so this is a common source. So this is our source and this is our gate. Okay, so in BJT counterpart, it is usually a common collector and a common gate a common base configuration. Okay, so your active device can either be BJT or FET. So in this example, we make use of FETs. Okay, so our Q1 is in a common source mode. Okay, so the output is impedance is coupled to the source of our Q2. Okay, so because Q2 is low impedance, okay, so Q1, because it is common gate, so it is characterized as low impedance, just like your our common base in our BJT counterpart. Q1 does not need to be neutralized. Okay, however, neutralization is also needed to reduce the noise figure even further. So our L2, okay, so our L2, our R1, and our C2 here, this circuit provides your feedback path for neutralization. Okay, so Q2 is common gate amplifier. So the input impedance, since it's a low input impedance characteristic, the input impedance requires no neutralization. Okay, so what is the advantages of cascoded compared with the other two that we have discussed earlier? So this offers higher gains and less noise than conventional cascaded amplifiers. Okay? So aside from these things, okay, so less noise. Okay, so we said less noise. So we have what we call low noise amplifiers, or LNAs. Okay, so LNAs are low noise amplifier, which generally include two stages of amplification along with impedance matching networks to enhance their performance. Okay, so usually low noise amplifiers are being used in high performance microwave receivers. Okay, so those types of receivers requires low noise amplifier circuit as input stage to the RF section to optimize their noise figure. Okay, so the first stage has a moderate gain and a minimum noise. So usually, first stage is low noise and high gain, and the second stage has high gain and moderate noise. Okay, so but having low noise and high gain for the first stage is difficult to achieve using single amplifier stages only. Therefore, usually this low noise amplifiers comes into different stages. Okay, so they are biased as class A again for the same reason to further improve the nonlinearity. So we make use of class A biasing and usually utilize silicon bipolar or field effect transistors up to approximately 2 gigahertz and gallium arsenide FETs above this frequency. Okay, so we make use of a special type of FET, which is your MOSFET. Okay, so your MOSFET is metal semiconductor field effect transistor. Okay, so this is a FET with a metal semiconductor junction at the gate of the device, and that semiconductor junction is what we call the Schottky barrier. Okay, so also integrated circuits. So those circuits that we have discussed earlier, they are in a form of discrete amplifier circuits. Okay, so RF amplifier circuits nowadays comes in integrated circuits form. Okay, so one example is the NESA 5200. So this is a wide band, unconditionally stable, low power, dual gain linear integrated circuit RF amplifier that is manufactured by Signetics Corporation. Okay, so usually it operates from DC to approximately 1200 megahertz and has a low noise figure. Okay, so the different advantages versus their comparable discrete implementations that we have discussed earlier, they don't need, okay, no external biasing components. They occupy little space on PCB, and the high level of integration improves its reliability over discrete counterparts. Okay, so it is equipped with a power down mode that helps reduce power consumption in application where amplifiers can be disabled. Okay, so here is an example. So here is an example of the block diagram of our NES5 SA5200. Okay, and what is inside the block diagram? So this is already the integrated circuit form. Okay, so wherein we can only see the pin. Okay, so if we're going to look at the inside, so this is the simplified schematic diagram of the inside of our NES5 SA5200. Okay, so these are made up of two stages. Okay, so two wideband amplifiers are biased from the same bias generator. Okay, so when disabled, the input signal is usually attenuated 13 dB, preventing receiver overload. Okay, so we said earlier that usually low noise amplifiers are made up of two stages. So therefore, in this type of example, so each amplifier stage has a noise figure of about 3.6 dB and a gain of approximately 11 dB. Okay, so several stages can be cascaded and used as an IF. Okay, IF is intermediate frequency strip, and the enable pin can be used to improve the dynamic range of your receiver. Okay, so for extremely high input levels, the amplifiers can be disabled. So the first stage that our signal will be encountering is our RF stage. And usually RF stage is made up of our preselector and our RF amplifiers. Okay? So following the amplifier stage or the RF amplifier stage is our mixer and converter circuits. Okay? So our mixer and converter stage is used, okay, or its purpose is to down convert the incoming RF or radio frequencies to as much lower frequency, which is our intermediate frequency. So we are not totally converting it to the information signal or to audio signal. So it will pass through a certain frequency, which is our intermediate frequency. Okay, so it will be the RF signal or the RF frequency will be down converted. Okay, so mixing the input of our mixer here. Okay, so the purpose of our mixer here is mixing our RF signal, okay, coming from your antenna, okay? And then from our local oscillator, so we have here our local oscillator, the two input signal that will be mixed is the frequency of our local oscillator, which is equivalent to sine of 2 pi FLT, and our RF signal, which is equivalent to sine of 2 pi FRT. Okay? So somewhat our mixer is a nonlinear amplifier which is similar to a modulator. The only difference is that our modulator is up converting our frequency while our mixer is down converting. So if you can still remember your modulator, it has two inputs, your information signal and your carrier signal. So in our mixer, in this case, we also have two inputs, our RF signal that is coming from the antenna and our signal coming from our local oscillator. Okay, so usually since it is a nonlinear amplifier, okay, it it has a nonlinear output, so it produces sum and difference, and usually the absolute difference, which is your FR, we have here your multiplying this. So this is a nonlinear mixing. So therefore, we have this two, okay, sum and difference, okay, output. So usually, the sum is being filtered out while we get your output. So the difference, which is frequency of your RF signal and the frequency of your local oscillator, will determine the intermediate frequency. Okay, so your intermediate frequency is the RF minus your local oscillator frequency. Okay, so we have here what we call balance mixer. Okay, so the output of our balance mixer is the product of our RF and the local oscillator. So what are the different circuits that is being associated with mixer and converter stage? Okay, so we have here your mixer is any nonlinear device that can be used. Okay, so although BJT and FET is generally preferable over a simple diode, a simple diode can do. Okay, so a simple diode can act as a filter, as a mixer, because technically a diode is a nonlinear device, but we prefer BJT or FET. Why? Because BJT and FET is capable of amplification, which is not being can't be provided by your diode. Okay, so the actual output signal from a mixer is a cross product frequency. Okay, therefore there is a net loss to the signal. Okay, so we call that net loss as your conversion loss or our conversion gain. Okay, so we call this as such because a frequency conversion has occurred, and at the same time the IF output signal is lower in amplitude compared to the RF input signal. Okay, so usually the conversion loss or your conversion gain is 6 dB or negative 6 dB. Okay, so this is the difference between the level of the intermediate frequency output with an RF input signal to the level of the IF output with an IF input signal. Okay, so there are different types of mixer circuit. Okay, so we have here the first example or the first circuit, which is probably the simplest mixer available, okay, other than the single diode mixer. So this is being used exclusively for inexpensive AM broadcast band receivers. We call this a self-excited mixer. Okay, so why do we call this as a self-excited mixer? Because the mixer excites itself by feeding energy back to the local oscillator tank circuit to sustain oscillations. Okay? We have here the circuit. Okay? So, the input for our circuit is your pre-selector. Okay, so our L1 and our C1 is our pre-selector circuit. So this is our pre-selector circuit here. Okay, so what is the input for our first self-excited mixer here? So the RF signals that is coming from the antenna, it is filtered by your pre-selector. Okay, that is the tuned circuit combination of our L1 and C1. So that is transformer coupled to the base of Q1. Okay, so Q1 is our active device. So Q1 is our active device. That means it provides amplification for our local oscillator. Okay, so our local oscillator is a tank circuit. So this is our local oscillator. So this is a tank circuit. C2 and I2. I think I have a wrong figure here. Okay, anyways, the local oscillator is a the frequency of the local oscillator is the resonant frequency of our tank circuit. Okay, so usually this is the difference between the RF signal and our IF signal, so which is your 455 kilohertz. So it offers poor selectivity and poor image frequency rejection because there is no amplifier tuned to the RF signal frequency, and only RF selectivity is in the pre-selector. Okay, so it is characterized with no RF gain, and the transistor nonlinearities produce harmonic and intermodulation components that may fall within your IF passband. Okay? So this is our self-excited mixer. Okay? So our next type of mixer is what we call the separately excited mixer. Okay? Wherein we have here, as you can see, our local oscillator and the mixer, each of them has their own gain already. So as you can see here, there is only one active device, which is our Q1, which provides our gain. Okay? So I think the figure here is what do you call this, somewhat turned upside down. Okay, anyway, I will just edit this one. Okay, so the separately excited mixer is just the same in operation. Okay, however, the FET is your active device for your mixer. However, your local oscillator has its own gain capability, unlike the previous one. That's why it is called separately excited. Okay? So usually this is used for high frequency HF and very high frequency VHF receivers. Okay? So we have here another type, which is your single diode mixer. Okay? So your single diode mixer is inefficient, somewhat. This is inefficient. Okay, because it has a net loss. Okay, so this is commonly used for the audio detector in AM receivers and to produce the audio subcarrier in television receivers. Okay, so when we discuss AM, TV. Okay, we will be learning there that television is composed of both AM and FM. The audio part of our TV transmission is AM. It is a special type of AM. So usually, it is commonly used for the audio detector in AM receivers and to produce the audio subcarrier in television receivers. Okay, so for a single diode mixer, again, it has two inputs. Okay, so what are those two inputs? So your RF input signal here and our local oscillator here. Okay, and then they are being mixed by our nonlinear device here is your diode. Since your diode is nonlinear device, therefore it is capable of nonlinear mixing. Okay, so when we say nonlinear mixing, it produces sum and difference frequency, wherein your IF output here is the difference in the frequency. Okay, so this is being coupled. Okay, so the output is being coupled by your L3 and C3. So this value here is tuned to our IF, or intermediate frequency. Okay. So lastly, we have a diode mixer. Okay, so balanced diode mixer. So the previous one is using a single diode mixer. So this is one of the most important circuits that is being used in communication systems. Okay, so balanced diode mixer is also called balanced modulators, or product modulators and product detector. So those are some of the terms that you might be encountering when you read other references. Okay, so this is used extensively in both transmitters and receivers for AM, FM, and many digital modulation schemes. Okay, such as PSK, that is phase shift keying, or QAM, okay, quadrature amplitude modulation. Okay, so the advantages of this balanced diode mixer is noise reduction and carrier suppression. So what do we mean by carrier suppression? We wanted to remove the carrier. Okay, so usually for a double sideband full carrier AM, or our what we call conventional AM, we what is detected by the receiving antenna is the carrier. Okay, so however, there are other types of AM that we will be discussing next, and some of the characteristics of those AM is suppressing the carrier. Okay, so therefore we will be discussing this balanced diode mixer when we wanted to suppress the carrier already. But since this is a conventional AM, okay, so therefore the carrier is still present in our receiver. Okay, so just like in our RF amplifier circuit, mixer and converter circuits can also be in a form of an integrated circuit. Okay, so we have here an example. This is Signetics NESA 602A. So this is a double balanced mixer and oscillator. Okay, so this is well suited for cellular radio applications. Okay, so this is the black diagram. Okay, it has a voltage regulator inside it, and you have an oscillator. So you have a local oscillator, okay, to be uh what do you call this, to be coupled with the RF amplifier that is to be received. Okay, so there are different in this figure, there are different input configurations. So we have here what we call the single-ended tuned input. Okay, so we have here the this is the single-ended tuned input. So we have here your balanced input. Okay, so this is our balanced input wherein we make use of your two inputs here. And finally, we have here your single input and single-ended untuned input. Okay, so this is an integrated circuit form of a mixer and oscillator if we do not want to build a discrete circuit, just like what have we have discussed earlier. Okay, so following the output of our mixer and converter circuit is our intermediate frequency. Okay, so our IF amplifiers. Okay, so IF amplifier circuits are very similar to RF amplifiers. They only differ in the frequency range. Okay, so IF amplifiers are usually in a lower frequency range. Okay, so IF amplifiers are relatively high gain tuned amplifiers that operate over a relatively narrow fixed frequency band. So we are already improving your bandwidth. How? By narrowing already our frequency band. Okay, so we are expecting a wider bandwidth in the RF amplifier circuit stage compared with the IF amplifier stage. Okay, so most of the receiver's gain and selectivity is achieved in the IF amplifier section. So it is easier to design and build IF amplifiers that are stable and they do not usually radiate and not easily neutralized. Okay, so because it is easier to build a stable amplifier when you have a lower frequency compared with those of higher frequencies. Okay, so there is a possibility of having no RF amplifier, but usually for IF amplifier stage, okay, generally it has between 2 or 5 IF amplifiers, and we usually call this several IF amplifiers as IF strips. Okay, so we usually call this IF strips. Okay, so we have here, if you're going to look at this one, this is a 3 stages IF amplifier. Okay, so our T1 and our T2 here, our two transformers here, are double tuned transformers. Okay, so later we will be explaining what are double tuned transformers. Okay, so we have here L1, L2, and L3. Okay, so L1, L2, and L3. So you can see they are topped. Okay, so they are topped to reduce the effects of loading. So we have already discussed what do we mean by the loading effects. Okay, so the base of our Q3 is also topped. Okay, from the top capacitors, from our top capacitors, C9 and C10. Okay, so our base is also topped between these two capacitors, C9 and C10, for the same reason. Okay, so C1 and our C6, where's our C6? So C1 and our C6 is what we call the So we call our C1 and our C6 as your neutralization capacitors. Okay? So for IF amplifiers, so usually they are in a form of what? They make use of inductive or transformer coupling. Okay? So what do we mean by inductive or transformer coupling? So this is the most common technique used for coupling IF amplifiers. Okay? So this is wherein your voltage is applied to the primary winding and is transferred to the secondary windings. Okay, so there are transformer coupled amplifiers are divided into two categories. Okay, so the first category is what we call the The first category is what we call the untuned primary and the tuned secondary. Okay? So this is an example of that. So our primary is untuned. So as you can see, we don't have a tank circuit here, just your L1. And our secondary side is tuned to a certain frequency within the value of your L2 and your C2 here. Okay? So we call this as single tuned transformers. Okay, so this is the frequency response, okay, or the response curve. This is the effects of coupling. So as you can see, depending on the types of coupling, we have the tight coupling, we have the medium coupling, and we have the loose coupling. So between the three types of coupling, the loose coupling has the most narrow bandwidth. Okay, so the narrower your bandwidth, that means you have the lowest coefficient of coupling. So if you can still remember, we have your coefficient of coupling, which is equivalent to, so the symbol for our coefficient of coupling is K, okay, and that is equivalent to the flux of our secondary side all over the flux of our primary side. Okay, so that is our coefficient of coupling. So the lower your coefficient of coupling between your two inductors, okay, the primary and the secondary flux of your inductors, you have a narrower bandwidth, but okay, as you can see, the signal amplitude is the one to be sacrificed. Okay, so you have to choose, what do you want, a higher amplitude but a wider bandwidth, or narrower bandwidth but lower amplitude. Okay, if you're going to remember, our main aim here is to reduce the bandwidth, because if we reduce the bandwidth, we are also reducing the noise in our system. So the way to loosen your bandwidth is, one way is by your coefficient of coupling. Okay, so in this type, okay, so in this example, we call this a we call this as your tuned primary, okay, because as you can see, your primary winding is tuned with your C2 capacitor here, and untuned secondary. Okay, so this is your untuned secondary. Okay, so this one is untuned primary and tuned secondary. So this one is tuned primary and untuned secondary. Okay, so the next category for transformer coupled amplifiers is our double tuned transformer. Okay, so this is an example of our double tuned transformer. As you can see, we have here tuned primary. Okay, so we are tuned at a certain frequency here because of the combination of your C and L. Okay, so as you can you remember, the frequency is equivalent to 1 all over 2 pi square root of LC. So we are tuned to whatever the value of your capacitors and inductors here. And we also have here your tuned secondary. Okay, so which is your L2 and your C2. And this is the response curve. So the meaning of the response curve is also the same as what we have mentioned a while ago. Okay, so we have here bandwidth reduction. So what do we mean by bandwidth reduction? Okay, so when several tuned amplifiers are cascaded together, the total response is the product of the amplifier's individual response. So as you can see, as additional tuned amplifiers are added, the overall shape of the response curve narrows and the bandwidth is being reduced. Okay, so for cascaded, if you can still remember, we are somewhat multiplying your gain, but the effect is you are lowering the bandwidth. Okay, because as you can see, we have here your zero point 0.7 here. Okay, so the cutoff frequencies here is equivalent to zero point 0.7. So if you further cascade that, okay, so if you further cascade that, the second amplifier also has a cutoff of zero point 0.7. So if we are going to multiply that, we have your first cutoff, which is equivalent to zero point 0.7. Excuse me. Okay, so your first cutoff is equal to zero point 0.7, while our second cutoff is also equal to zero point 0.7. So multiplying these two cutoff frequencies, so that will give you around, what is that? So we have here zero point 0.7 multiplied by zero point 0.7, so that is around 0.49 or rounded up to zero point 0.5. So therefore, your bandwidth now instead of zero point 0.7 becomes zero point 0.5. So somewhat it is being narrowed down. Okay? So adding another cascading another stage, again, you will be multiplying another cutoff which is equivalent to zero point 0.7. So zero point 0.5, okay, if we're going to multiply zero point 0.5 by zero point 0.7, so that is around approximately 0.35. So 0.35 as your cutoff point. So therefore, further narrowing down your bandwidth. So adding, okay, additional IF amplifiers, cascading additional amplifiers somewhat improves your bandwidth, okay, by bandwidth reduction. Okay, so usually intermediate frequency comes in what we call, okay, IF cans. Okay, so what is IF cans? So they are specially designed tuned circuits in groundable metal packages. Okay, so we have here the physical. Okay, so we have here the physical diagram for an IF can, okay? And then we have here the schematic diagram for untapped coil, okay? So we have here an untapped coil, and this is our schematic diagram for tapped coil, okay? So this is a type of an amplifier circuits, okay? So integrated amplifier, okay, IF amplifier circuits may also come in an IC form. Okay, so we call this as your integrated circuit IF amplifiers. So we have here an example, your CA3028A. So this is a differential cascaded amplifier designed for use in communications and industrial equipment as an IF or RF amplifier at frequencies from DC to 120 megahertz. Okay, so in this, okay, so usually this type of integrated circuit IF amplifiers have since in universal acceptance in mobile radio systems such as two-way radio. Okay, so of course it has the advantages of having smaller in size and low power consumption. Okay, so we have here the schematic diagram, and what is inside is a cascoded. Okay, so as you can see, you have a cascoded amplifier configuration inside the integrated circuit. Okay. So, following the intermediate frequency section, okay, so the next stage is our AM detector. Okay, so what is our AM detector? What is the purpose of your AM detector stage? So, your AM detector is there, okay, its purpose is to demodulate the AM signal and recover or reproduce the original source of information. So, we also call this as the first detector, okay, because somewhat we are changing your frequency from the IF frequency to the original source of frequency or your audio frequency or the information frequency. Actually, the first detector, if this is the second detector, your first detector is the mixer and converter, because in there you have down converted your RF to IF. So we are furthermore down converting our frequency this time from IF to the information signal frequency. Okay, so the recovered signal should contain the same frequencies as the original information and have the same relative amplitude characteristics. So actually we are detecting the amplitude because AM is characterized as the change in the amplitude. So what we are looking through at this one is the detection of the difference in the amplitude. . 。 . 。 . 。 . 。 . . 。 . . 。 . . 。 . . . . . 。 . . . 。 . . . . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . .
。 .
So we have here an example of an AM detector circuit. Okay, so we call this as your peak detector. This is a nonlinear mixing, okay? So a nonlinear mixing occurs when two or more signals are applied to its input. Again, this is a simple non-coherent AM modulator, and it is demodulator rather, and it is just like your modulator circuit because it has two inputs. However, our nonlinear mixing here, or our nonlinear device here, is your diode. So the input for our linear or our peak detector is the IF frequency coming from your IF amplifier stages. Okay, so the output contains the original input frequencies plus their harmonics and their cross products. Okay, so for example, okay, so the output will comprise the three input frequencies, which is the harmonics of all three frequencies and the cross products of all possible combination of the three frequencies and their harmonics. So for example, we have a carrier frequency of 300 kilohertz, and we have a modulating signal of 2 kilohertz. Okay, so what is the output for our peak detector? So the output is the input frequencies plus their harmonics and their sums and difference. Okay, so what are those? So the carrier is still present. Okay, so the sum, what is the sum? So the sum is your 302 kilohertz. Okay, and then what is the difference? So you have your 298 kilohertz. So you have your 298 kilohertz, okay? So they are present, okay? And then, okay, so we get their differences because we are filtering the sums, we are just getting the difference. So what is the difference? So we have here 300 kilohertz and we have minus 298 kilohertz. So that will give us 2 kilohertz, okay? Also 302 kilohertz minus 300 kilohertz. So that will give us 2 kilohertz. So we have 302 kilohertz minus 298 kilohertz. So we have 4 kilohertz. Okay. So, however, okay, the filter here, okay, so the combination of RC here is somewhat acting like a filter, and this is designed in such a way that it will only accept frequencies that is equivalent to 2 kilohertz. So therefore, other frequencies will be filtered out, and the only thing that we're going to receive and that will enter, okay, so that will enter your audio amplifier stages are those frequencies equivalent to 2 kilohertz only. Okay, so we have here we call that circuit as a peak detector. Okay, so what does your peak detector do? Okay, so because the relative amplitude characteristic of the upper and the lower side frequencies and the carrier difference between the carrier are either the same, so it's either we choose the upper or the lower. So in this case, we are choosing the lower frequencies, which in we get the differences, which is equivalent to 2 kilohertz. Okay, so peak detectors. The RC network is a low-pass filter which only passes the difference frequencies. So only the difference, which is 2 kilohertz, are passed on the audio section. Okay? So for practical purposes, the original modulating signal is the only component that is contained in the output of your peak detector. So actually, we call this in different names, okay? So, we can call it as a diode detector. Why diode detector? Because the nonlinear device that is being used here is a diode, okay? So, we can also call this as a peak detector. Why? Because it detects the peaks of the input envelope. Okay, and we can also call it as a shape or envelope detector because it detects the shape of the input envelope. Okay, so even though the IF frequency is a lower frequency, but still it is in the same envelope form like in the RF frequency. Okay, so the carrier signal capture the diode and forces it to turn on and off. So the purpose of your diode here is just to forward or be reverse bias. So when it is forward biased, we have an output. When it is reverse bias, we don't have an output. Okay, so the turning on and off is what we call rectification. Okay, synchronously, both frequency and phase. Okay, so that is the function of our peak detector. Okay, so this figure here shows the three, okay, this is the input waveform in a form of an envelope, okay? So this is your diode current waveform and this is your output voltage waveform. So very simple. So what is the purpose of your diode? So at T is equal to 0, okay? So that means your diode is in the reverse bias mode, so it is not functioning. Therefore, our current there is equal to 0. Our ID is equal to 0. And if our ID is equal to 0, we don't have an output voltage. And your capacitor is not yet charging. Okay? So, once your diode reaches its threshold voltage, okay? So, once the input here reaches the diode's threshold voltage, so what is that? So it can either be its barrier potential, so it can be zero point 0.3 for germanium or it can be zero point 0.7 for silicon. Your diode starts conducting. Okay, so as your diode starts conducting, you have now your current. Okay, and that specific current correspond to the amount of voltage that can be charged through your capacitor. So if this is equivalent to zero point 0.3 or zero point 0.7, for example, your output voltage here will also be equal to zero point 0.3 or zero point 0.7. Okay, so since during the negative half your diode is in the is in the reverse bias, so we only have the positive peak here, the positive half cycle. So it was rectified. Okay, so somewhat your signal was rectified because of your diode. Okay, so if we have a maximum voltage here, your capacitor charges to a more higher value, to a maximum value. Therefore, we have an output which is equivalent to that higher maximum voltage. So as you can see, our output voltage waveform somewhat is the same with our input voltage of our AM here. Okay, so that is the purpose of your positive peak detector. Actually, it is a positive peak detector because uh, we detect the positive side. But when you reverse the diode, so the diode will be forward biased at the reverse cycle. So therefore, we will be having the negative side of your waveform. So we now call that the negative peak detector. Okay. So we have here some detector distortions. Okay. So if this is our input waveform, we have what we call the rectifier distortion and the diagonal clipping distortion. So usually it has something to do with the value. Okay, so it has something to do with the value of your RC. Okay, so take note that your RC is your time constant. It detects whether your capacitor is charging faster or slower. Okay, so when your capacitor is charging too short, okay, so therefore since it is charging too short, on the turning on and off of your circuit or of your diode is very very short or very very long. So therefore we have here what we call the rectifier distortion. Okay, so most of your input signal is being cut off. Okay, so however, when your capacitor is or your time constant is very very fast, okay, so we end up with diagonal clipping. So that is when when your RC is, it takes very very fast to charge and to being discharged. Okay, So we also have what we call, so aside from those circuits, we also we have what we call the automatic gain control circuits. Okay, so AGC, or the automatic gain control circuits, they automatically increases the receiver gain for weak RF input levels, okay? And automatically decreases the receiver gain when a strong RF signal is received. Okay, so actually this automatic gain control circuits compensates for minor variations in the received RF signal level. Okay, so when you have a weak signal, okay, when you have a weak signal, it can be buried in a receiver noise, so it becomes impossible to detect. However, when you have a very strong signal, it can override your RF or your IF amplifiers and can produce excessive nonlinear distortion and even can drive your amplifiers to saturations. Okay, so this is a compensating device or a circuit for minor variations, for weak signals that cannot be detected, or for higher signals that can saturate your amplifier circuits. Okay, so automatic gain control signal is a form of a degenerative or negative feedback. Okay, but do not confuse it with a form of automatic volume control. So it is not a volume control. Okay, so this is to allow a receiver to detect and demodulate equally well. Okay, so signals that are transmitted, for example, from different stations whose output power and distance from the receiver vary. Most particularly, for example, you are in a car, okay, so you are traveling, so your distance varies, so at the same time, the output power coming from the transmitter also varies. So to compensate these variations, we use the automatic gain control circuit. Okay, so we have here an example of an AM super heterodyne receiver with simple automatic gain control. Okay, so this is used in most inexpensive broadcast radio receivers. Usually, your AGC correction voltage comes after your IF amplifier stage. So mostly, this is already in the audio amplifier or in the audio detector stage. Okay, so this is an example of a simple AGC. Okay, simple automatic gain control. So the AGC bias begins to increase, okay, as soon as the received signal exceeds the thermal noise of the receiver. Okay, however, when we do this, the receiver becomes less sensitive. Okay, so to compensate to that, okay, so to compensate to that, we have what we call the delayed AGC. Okay, so the problem with the simple AGC is that the receiver gain is immediately affected. Okay, once the temperature heats up, the receiver gain is immediately affected. So we have a solution for that. So we have here the delayed AGC. So the delayed AGC prevents the AGC feedback voltage from reaching the RF or IF amplifiers until the RF level exceeds a predetermined magnitude. Okay, so in this, there is a comparator. Somewhat you are comparing to a certain value. Okay, so the receiver gain is unaffected until the AGC threshold level is exceeded. As long as it is not being exceeded, okay, the automatic gain control circuit will not function. Unlike with the simple AGC, once there is a change in the input, the receiver gain is immediately affected. Okay, but still the simple and delayed, they still have a problem because the simple and delayed, they are both form of post AGC. That means they are detecting the problem when the problem already occurred, okay, and they are being in a position at the audio. So therefore, what if the problem is not detected? So therefore, there is already a problem in our audio stage. Okay, so to compensate for that, we have what we call forward AGC. Okay, so forward AGC, the received signal is monitored closer to the front end. Okay, so as you can see, your AGC is here already, and we will not be waiting at the audio section wherein there is a possibility that the signal is already very weak or very strong. So we will be doing the solution, or it is not a post automatic gain control, rather it is forward. Okay, so the received signal is monitored closer to the front end of the receiver, and the correction voltage is fed forward to the IF amplifiers, not after the IF amplifiers. Okay? So another type of circuit that we can see in our receiver circuits are what we call squelch circuits. Okay? So what do we mean by squelch circuit? Okay? So to quiet, this is used to quiet a receiver in the absence of the received signal. Okay? So all of the stations, okay, are transmitting their carrier regardless or whether there is any modulation. Okay, so the carrier without a modulating signal is a hissing sound, zzz, so like that. Okay, so when your receiver is tuned to a band wherein there is no modulating signal, usually it is noisy. Okay, so to prevent that, some high level receivers use squelch circuits. So this keeps the audio section of the receiver turned off or muted in the absence of a receive signal. Okay? So another type of circuits that may be seen in your AM receiver are noise limiters and blankers. Okay? So noise pulses are generally large amplitude, short duration signals. Okay? So they can be eliminated using our diode limiters or clippers, if you can still remember in your electronics one. Okay? So it can remove sporadic high amplitude noise transients of short durations, such as an impulse noise. Okay, so usually this is placed in the audio section of our receiver. Okay, we also have what we call a blanking circuit. So this detects the occurrence of high amplitude, short duration noise spikes. Okay, then mutes the receiver by shutting off a portion of the receiver for the duration of that specific pulse. Okay, so usually they are being placed at the receiver side. Okay, so we also have a complete package. Okay, so we have a complete package of linear integrated circuit AM receivers. So we have here an example. Okay, so we have the LM1820 linear integrated circuit AM radio system. This is made up of RF amplifier. Okay, so we have already discussed the RF amplifier stage. We have the mixer. Okay, so this is your mixer. You have your local oscillator here, and you have your IF amplifier section here, or stages. Okay, so instead of having different or several individual AM receiver circuits, we can instead make use of a linear, okay, or an LIC integrate AM receiver. Okay, although this is not yet complete because it stops with the IF amplifier. Okay, so therefore you need another linear integrated circuit or LIC audio amplifier. Okay, and of course speaker. Okay, so you have to have a speaker so that you can have the complete function of a receiver circuit. Okay. So we have here a double conversion AM receiver. So a double conversion AM receiver uses two intermediate frequencies. Okay, so as you can see from the block diagram, you have your first IF, you have your second IF. Okay, so this is what we call a double conversion AM receivers. Okay, so we have the net receiver gain. Okay, so we usually talk about the gain. So we have the RF gain, you have the conversion gain, you have the IF gain. So usually they are in decibels. Okay, so what do we mean by the net receiver gains? Because not all of them are gains. Okay, so some are in a form of an attenuation. Okay, so we need to get the net receiver gain. So the net receiver gain is simply the ratio of the demodulated signal level at the output of the receiver, which is audio, to the RF signal level at the input of your receiver. So simplifying further, this is simply the difference. So if we are talking about decibels, so this is simply the difference between the audio signal level in dBm and the RF signal level in dBm. Okay? So it is the sum of all the gains in the receiver minus the sum of the losses. Okay? So in formula, we have here the net receiver gain is equal to the gains, sum of all the gains in the receiver. So what comprises those gains? So those are your RF amplifier gains, you have your IF amplifier gains, and you have your audio amplifier gains, minus the losses. Okay, minus the sum of the losses. So what are the losses in your in your AM receiver circuit? So the losses comes from the pre-selector loss, you have your mixer loss, and you have your detector losses. Okay, so if we're going to look at this one, your RF signal coming from the antenna going to your speaker here as your audio output power experiences loss and gains. So all we have to do is to just subtract those losses from the total gains to get the net receiver gain. Okay? So, what are we talking about now? So, what is the practical application of these things that we are talking about? So, I have here some receiver examples. Okay? So, these are the circuit wherein we make still use of what? Discrete components. So, they are form of a discrete components because you can also, this is a combination of integrated circuits and your discrete components. So usually this is your transformer for coupling purposes. Okay, so transformers are not yet embedded in an integrated circuit. Okay, or some, they are already in a form of an integrated circuit. Okay, so these are some receiver examples. And these are your example of a radio receiver wherein you still make use of the mechanical tuning, and you have here your antenna so that we can detect your RF signal here. Okay, so depending on what type of RF signal that we are going to make use, and we are going to tune to our favorite specific band of frequency. Okay, and then we have no mechanical tuning. Okay, so this is also your mechanical tuning here, but nowadays in your car, so you have already what we call digital, okay, tuning. So this is an example of an AM receiver wherein this is capable both for AM and FM. Okay, so that's it for our AM receiver circuits. Okay, so thank you very much for listening, and don't forget to hit the like button. Okay, so goodbye and God bless. Okay, bye.